to join everyone else in saying thanks to the organizers for inviting me to give this talk. I really enjoyed and learned a lot from the talks and the discussions so far. So this has been really beneficial for me. So today I want to talk about bound nucleon structure with tag DIS, and I will say that I'm actually missing a couple references in these slides, but they will be updated later today. So just to kind of reiterate some of the points that Ellie made yesterday, nucleons in the nuclei are bound by on order of 1% of the mass. So a nucleus has a mass of 1 GeV. Most of this is dynamically generated by by QCD. Then you have nuclei that have typical binding energies of less than 10 MeV per nucleon. And so your naive intuition might say that this MeV scale binding shouldn't be impacting the GeV scale part-time dynamics within the nucleon, but the fact is it does. And so this is the famous plot from the EMC collaboration showing the per nucleon structure function ratio of iron to deuterium deviates strongly from 1. And having done my PhD research on DIS and most of my postdoc work on DIS, I've given and heard countless talks on the EMC effect. And I have to say that one of them that has kind of stuck out as being really special was a talk by Hugh Montgomery at a workshop in 2021 on SRC and EMC research. And so many years before he was the director of JLab, he was a staff scientist at CERN, and he was actually at CERN when this was discovered. And so hearing his kind of personal account of everything that was going on behind the scenes was very cool. So if you're interested in that, this is a link to his slides. You can take a look at it. So this is from 1983. This is the discovery. This is a paper from much later, from a couple of years ago. And I'm choosing this one because it kind of summarizes all of the experimental efforts that have been done since then. But this one paper didn't do all of the measurements. There was work at SLAC. There was work at Jefferson Lab to study the EMC effect in a wide range of nuclei. And so a huge amount of experimental effort has been put into this. So the bottom line is just that the nuclear structure function is not simply equal to the sum of the constituent nucleon structure functions. Now, one of the things that Hugh mentions in his talk is that he was discussing the result shortly after it was published with Roy Holt. And Roy quipped that the EMC folks really actually were particle physicists. They weren't nuclear physicists, and that the nuclear physicists would have the whole problem sorted out within a few months. That was Roy's perspective. And so certainly after this was published, there was a flurry of people coming forth with explanations to explain this observation. And I'm going to summarize a couple of those here. So first of all, the most basic thing you could imagine is that you have this deviation from unity because the nucleons are moving. And this was actually not like a post-diction. This was something that was pretty well known before the EMC discovery. So the earliest reference I can find to this is a paper by West from 1971. So this is 12 years before the EMC results. This is only 3 years after the actual SLAC experiment that discovered partons. And it has this kind of ominous sounding name that the total neutron cross-section may not be what it seems to be. And he was cautioning people who at the time were trying to make statements about the neutron based on deuteron measurements. And he is cautioning people that you need to focus on a subtlety for what is perhaps the simplest correction, namely that due to Fermi motion. The nucleons are moving within the nucleus, and this can obscure what you see. And so as I said, this was actually known before the EMC measurement. And so in the EMC publication that I just showed, they actually included several theoretical curves that account for this motion of the nucleons. But as you can see, they clearly are not able to explain this deviation. And so this is kind of ruled out as being, this is an important effect, but this cannot explain the EMC effect that's been observed. Another possible explanation was non-nucleon degrees of freedom. So if you have these nucleons within the nucleus and they're exchanging pions, you can have this pion cloud surrounding your nucleon, and maybe when your electron comes in and scatters from your nucleus, instead of scattering from the nucleon, you actually scatter from one of its pions. My understanding is that there were several models based on this that were actually successful in explaining the EMC effect. However, these models also predicted an enhancement in the C quarks of the nucleon that would show up as an enhancement in the Drell-Yan ratio. And so this is one of my missing references. This is a paper from Fermilab from 1990, where this is the Drell-Yan ratio for I think it was dimuon production, this was the prediction that you would get if the 100% of the EMC effect was caused by pion excess. And you can see that this ratio is very clearly below that. So the Drell-Yan measurements kind of eliminated this as a possible sole explanation of the EMC effect. And so the kind of idea you're left with is that the actual parton structure of the bound nucleon is different. You have a free nucleon, this has some parton structure, you put it in the nucleus and it's different. And so here we are 40 years later, and we still don't know what is causing this. So there are kind of two big implications of that statement. The first one is a very fundamental implication, and that is that if we want to pinpoint the origin of the EMC effect, we have to have some method of separating kind of the conventional nuclear effects that we understand from exotic effects that could be causing this modification. The second implication is a little bit more practical, and that's that we have to use neutrons bound in a nucleus to learn about free neutron structure. And so somehow we have to be able to account for these nuclear effects if we want to be able to make a statement about what's going on inside of a free neutron. And so
sorry, stupid question.
Yeah.
What do you mean conventional, and what do you mean by exotic?
Well, so I mean, for instance, Fermi motion. This is something that's like that is more or less well understood, and like when you have a model to try to account for nuclear effects, this is like a standard thing to include in your measurements, or to include in your kind of theory calculation. But this cannot explain the observed modification.
Sure.
And so I guess when I say exotic, I mean something that you could say, okay, it's strongly interacting SRCs. That's that's
something that is not obvious. Or...
Exactly. Yeah. Okay. Yeah. So this was maybe this is just a kind of there's nothing specific here. Like exotic isn't supposed to evoke a certain type of physics. It just means something that's not understood, because there really is no consensus on what is causing this modification. And so as I said, many of the things that we kind of know, quote unquote, about the nucleus go into calculating the nuclear wave function. And you can kind of split the nuclear wave function into two pieces. And this is, was touched on yesterday in yesterday's talk by Ellie. And that's that, you have this low momentum part of the wave function where you have these nucleons that are kind of in a mean field. They have large separation, moving with relatively low momentum, and they interact, like a single nucleon kind of interacts with the mean field of the A-1 system. When you go up above the Fermi momentum, these are where you find these short-range correlated nucleons. And so these are nucleons that have very small separation, they have very large momentum relative to each other, and also they populate this high momentum tail in the nucleus. The pairs interact very strongly with each other, and in fact, you can kind of factorize it from the A-2 system. So when these nucleons are in this short-range correlated state, they really don't care about the rest of the nucleus. They're interacting so strongly with each other that that's basically the only thing that they see. Now one limitation, most of what we know about the EMC effect has come from inclusive DIS. And inclusive DIS gives you the average structure of the nucleus. And so this is, as Abe was talking about in his talk, this is a very attractive method of performing measurements, because by just measuring the scattered electron, you can reconstruct basically everything that there is to know about the interaction. You can calculate Q squared, which tells you the scale of the interaction. This has to be high enough so that you're actually resolving the quarks within the nucleus. And then you have the kind of dynamic part, which is X Bjorken, which describes the momentum fraction of the quark that took place in the scattering event. The limitations of this, though, are that first of all, you're integrating over the entire nucleus. You're scattering over off of all the neutrons, all the protons. You don't know which one you're scattering off of on an event by event basis. You're also integrating over the entire nuclear wave function. You're scattering off of low momentum nucleons and high momentum nucleons. And so you're getting a very average picture. The other issue is that your variables, these inclusive variables, are actually kind of smeared out by Fermi motion. So you kind of have a small loss of resolution, based on the fact that your nucleons are moving. And if you're, obviously the wave function is dominated by low momentum nucleons. And so in most cases, this just means that your variables just smeared out a little bit. But if you do happen to scatter from one of these high momentum nucleons, this can actually cause a sizable shift in the kinematic variable that you reconstruct. And I'll show an example of that later. So tagged EIS can actually provide the remedy to some of these problems. And so when I say tagged EIS, what I mean is that we're not only detecting the scattered electron, but we're also detecting a spectator nucleon, a nucleon that was in the nucleus, that was not the nucleon that was struck by this virtual photon, but that kind of comes out of the nucleus after the interaction. And using this, you can actually reconstruct what parts of the initial nuclear state at the time of scattering. And so essentially, like for instance, if you're measuring in deuterium, you have a proton and a neutron. So number one, based on whichever your spectator nucleon you detect, you know what your active nucleon was. So if you detect a neutron, it must have been the proton that was struck. And the second thing is that in deuterium, it's a very simple two-body system. So it's like or relatively simple two-body system. And so you have these two nucleons that are always correlated. So if you measure the outgoing spectator, you're able to reconstruct what the momentum of the initial nucleon within the nucleus was. And so this is what actually allows you to do measurements of nucleon structure as a function of the spectator momentum, which allows you to kind of take this differential look at structure across the nuclear wave function. Another thing that that tagging allows you to do is account for the nucleon motion, which can essentially get rid of this kind of smearing that happens based on the Fermi motion. So just some of the variables that you can reconstruct with tagged DIS. There's alpha S, which is the light cone momentum fraction of the spectator nucleon. This is not the strong coupling. This has been a source of confusion in previous talks. It's completely independent of that. And basically, it's just the energy of the spectator minus the longitudinal component of its momentum relative to the Q vector. And then you can define, your W becomes this variable called W prime. Some tagged DIS experiments refer to it as W star or W asterisk. And X Bjorken becomes X prime. And in both of these cases, they're defined kind of the same way that you defined it in the inclusive case. It's just that your initial, target momentum, instead of simply being the mass of the particle, it includes, the actual motion. And so in the case of X Bjorken, or the tag scaling variable X prime can approximately be represented as X Bjorken divided by 2 minus alpha S. So you see that for alpha S of 1, you get this is a standing nucleon. You just have X Bjorken, but then as alpha S increases, you start causing a larger and larger shift in what the actual X is. And so what this allows you to do is essentially turn the wave function into a laboratory for nucleons of various off-shellness. So if you isolate kind of the low momentum part of the nucleon, you can study weakly interacting quasi-free nucleons. These are the nucleons in the nucleus that are the weakest bound. And then you can go to the high momentum part of the nucleus, or part of the wave function, where you study strongly interacting short-range nucleons. And so this is actually like a very powerful tool for being able to kind of get a differential look at the structure of nucleons bound in the nucleus. So one thing that's very important when thinking about trying to perform these types of measurements are trying to mitigate the effects of final state interactions. So you have this very violent process where you have a very high energy virtual photon that comes in and blows apart this, whatever your active nucleon is. And you want your spectator to kind of escape from the nucleus and be detected without interacting with all of this DIS debris. You want, because that will obscure, your ability to reconstruct what was happening inside the nucleus. So this DIS, your final state, largely goes in the direction of the Q vector. So one way that you can try to avoid these effects are by looking at spectator nucleons that are going very backward relative to Q. The second thing is that FSI calculations, at least my, what the best knowledge that we've been given by theorists is that they're largely independent of X. And so another way that you can mitigate the effect of FSI on your observable is by looking at ratios of kinematic points. So if you're looking at the X dependence, take a ratio of high X to low X or something like that, and the FSI will supposedly mostly cancel out. So what I'm going to do is kind of just like highlight a variety of tag DIS efforts, starting at the low momentum part of the wave function and moving up to the high momentum part. So we're going to start with BONUS, the barely off-shell neutron structure experiment, which used tag DIS to get the free nucleon structure function ratio F2n over F2p. Then I'll talk about how you can get the spin structure of the neutron with tag DIS at the EIC. Then moving up above the Fermi momentum, I'll talk about 3 experiments, deep span and LAD, that attempt to study the structure of high momentum bound nucleons. So let's start with BONUS. I'll start by just saying a few words about why this ratio F2n over F2p is so important. So the limit of this ratio as X Yorkin goes to 1 is sensitive to the D over U ratio of the nucleon, which kind of puts constraints on the mechanisms that spin flavor symmetry is broken. And in addition to that, it provides critical constraints on the PDFs, as I said, mostly the ratio of D over U, which is a leading, one of the major sources of uncertainties for theoretical predictions at like high energy colliders. So by constraining these PDFs, we can reduce the uncertainty in predictions for these experiments. Historically, the preferred method for getting this ratio F2n over F2p was to extract the ratio from nuclear structure functions with corrections for nuclear effects. So you measure the deuteron or some other nucleus, and you subtract the proton, account for nuclear effects, and say what's left must be the neutron. However, the problem is that that's very model dependent. I mean, so you essentially you're trying to separate 2 effects. 1, what is the difference between the neutron and the proton? And 2, what are the nuclear effects? And so there's always some intrinsic model dependence to trying to do this. The other method that can be used is to use tag DIS to extract the structure of barely off-shell neutrons in deuterium. And so that is what BONUS did. So BONUS was an experiment that ran in Jefferson Lab Hall B. This was during the 6 GeV era. So they ran at 3 different beam energies that were between 2 and 5 GeV. Their target was a thin deuterium gas target. The scattered electron was detected in the CBAF large acceptance spectrometer, and the recoiling spectator proton was detected in a dedicated radial time projection chamber that was constructed just for this experiment. And so the kind of relevant ranges of momentum that they were singling out is shown here. So you can see that this is very, very close to the very low energy or low momentum in the deuterium wave function. Before I show the results, I wanted to show the invariant mass spectrum that they measured, and I think this might be one of the best kind of single image explanations for tag DIS that exists. What you're seeing here is the two invariant mass spectra. The first one is just reconstructed using the scattered electron, and the second is reconstructed using the scattered electron and the recoil spectator. And so this allows you to take into Fermi motion into account. And so the open the hollow points are just the inclusive W. And what you see is that these, the nucleon peak, the delta, they're kind of like really smeared out. Whereas once you start accounting for the motion of the nucleons, using the spectator proton, these peaks suddenly sharpen way up. And even up here, you see that you can even start to resolve certain resonances that are completely washed out in the inclusive case. And so this is like a really good example of like how this improves the picture that you see by using the information from the spectator. So this is the result that they got.
Excuse me,
Yes.
maybe it's too early question. What is the nature of those resonances? Is understood? What are those resonances?
Oh yeah, I mean, so I think this is the, I mean, so this is the just the nucleon, scattering like the quasi-elastic peak. This here is the delta resonance. I'm not sure what these higher ones are.
Like the proton mass, like nucleon mass.
Yeah, so this is, yeah, you see, so this is the nucleon mass, and then this is the delta.
So this is associated with particle reduction.
Excitation.
Yeah, excitations. And then you, as you go high enough into W, then you kind of enter this inelastic continuum.
Yeah, okay.
Did anyone overlay this with the known spectrum of the proton? Because this has been measured like very, very precisely in other measurements, right? All these nucleon resonances, they are very well known.
Right. Except, I mean, this is just. Right, except if they're measured, if you're still measuring them inclusively, then you're still going to suffer from this kind of smearing out that's caused by the Fermi motion. So
yeah, so my question is there anything you can learn about the nucleon structure from this?
oh,
Is there any peak that they, because you say you
Oh, that's a good
things,
question.
but
I
then
don't
try
know.
to
Yeah.
Those are resonances of the neutron.
yeah. So that's a good point. That this is the neutron because you're tagging on a spectator
and
proton.
that you don't get easily.
Right.
Yeah,
Right.
except the isospin.
Yeah, but then you can actually study isospin violation in.
Yeah, well, what is this precision? In general, it's a unique way to look at the excitation of a neutron.
Yeah, it's pretty cool.
So these are the results that they got. There are 3 different sets of points here. With some looser cuts on W or looser cuts and to tighter cuts. So obviously, the tighter your cut on W is, the less the less access you have to higher X. And so those are the 3 curves shown here, or 3 sets of points. They compare against the prediction from the CJ, global PDF bits. But so at the time, this maybe isn't the most competitive measurement, except it's the first attempt at trying to be independent of extracting with model corrections. And so I will say that bonus 12 actually has recently collected data over the past couple of years with the upgraded 12 GeV electron beam at Jefferson Lab. And so they don't have results yet, but they will essentially be an extension of this at higher beam energy. So I also wanted to kind of show how this stacked up against the latest and greatest in extracting F2N over F2P from using nuclear corrections. So this was actually what I worked on for my PhD. The marathon experiment measured the ratio of helium-3 to tritium. And from that, they used a model to extract F2N over F2P. So the kind of the advantage here to using helium and tritium instead of deuteron and proton is that you only have to account for the relative nuclear corrections in these A = 3 nuclei. If you're using the deuteron and the proton, you have to account for 100% of the nuclear corrections. Whereas when you use the ratio of A = 3 nuclei, you only have to say, okay, what is the relative nuclear effect in one versus the other? Most models predict very similar nuclear effects for helium and tritium, and so your correction is actually very, very small. It's still model dependent, but that was kind of the motivation for doing it this way.
Sorry.
Yeah.
So the author, I just noticed this is the second measurement I see in like in the past year that actually people measured tritium, which for decades I think nobody was touching.
Right, yeah, so I mean,
So
the thing.
what changed that?
The thing that we were told was that this is like a once in a generation opportunity. And so when Marathon was like the flagship tritium experiment, but when the decision was made to implement a tritium target, there were a bunch of other people that were interested in performing measurements.
So benefit
And
all the
so
same.
there were many experiments that ran with this target.
It's very
Driven by
difficult to
overcoming
handle,
the
right?
technical
Because it requires some measures. some
Right, so
safety
actually the
and-
way it was done was that a sealed gas target cell was designed by the target group at JLab. They sent this to Savannah River National Lab. Savannah River put the tritium in the target, sealed it up and sent it back to JLab. So JLab never actually touched the tritium. They only handled this sealed target cell. And yeah, there were a lot of limitations on the beam current and how you were allowed to run, et cetera. Yeah, so this was quite a monumental achievement, and a lot of experiments tried to take advantage of this target.
Can I say one thing? It's very similar to what was done at Trick, actually. They wanted to cancel systematics, and so they took ratios of isobars. That's exactly the idea here.
So here on the right, I mean, this is the exact same curve that's shown here, only now it's shown against the bonus points. And so you can see that they're largely consistent. And so it's going to be very interesting to see what bonus 12 measures, because they should be able to get up to higher X here. Okay, so now moving on. So now we're going to stay at the low momentum part of the wave function, but now we're going to go to the EIC, which Abe talked about on Tuesday. So just a quick word about how you measure nucleon spin. So you have access to the polarized PDFs by measuring these so-called double spin asymmetries, where you have a polarized electron beam, polarized ion beam, and by measuring different orientations of them, you can extract these asymmetries. And this A1 is what you essentially try to measure from a combination of these two double spin asymmetries. And this is approximately equal to the G1 structure function, which is the polarized PDFs. And so this gives you information. This is how you extract the spin content of the nucleon. Now, historically, helium-3 has been the favored kind of nucleus for extracting neutron spin, because when you have polarized helium-3, the neutron carries most of the spin. So with polarized helium-3, the neutron polarization is about 87%. And so, historically, what's been done is you essentially measure the double spin asymmetry of helium-3, and then using that, you subtract off the effects of the proton to isolate the neutron A1N. And the issue here, though, is the same thing that happens with F2N over F2P, is that this is a very model-dependent correction. And so you end up having very large uncertainties from this model dependence. What you can do is you can also extract the neutron spin structure using double spectator tagging. And so in this, you still use polarized helium-3, but instead of tagging on just one recoil spectator, you actually tag on both of the protons. So you have to detect the scattered electron and two protons. And this is the only way that you can ensure that the neutron was actually the active nucleon that you scattered off of. And so what you want to do is you want to require that these two protons have very low momentum, so that you're scattering off of this very low momentum neutron in helium. And then you can extract the spin structure with much reduced model dependence. So so this is kind of illustrating the kind of phase space that you're trying to isolate. This is the magnitude of the vector stum of the two spectator protons, and you want this to be less than 0.1 GeV. And so the problem is that this is not feasible at a fixed target facility. Trying to measure, if you have a fixed helium-3 target, trying to measure these two low momentum spectator protons is basically impossible. And so that's why the EIC is so special, because these low momentum, these protons that are low momentum in the ion rest frame are really, highly boosted because it's, in this, many GeV beam. And so what this means is that these spectator protons now have large enough momentum to be able to reliably detect. And so this is just a schematic. This is kind of a schematic cartoon of the central detector at the EIC, which would be responsible for detecting the scattered electron. But then because your protons are so boosted, they go they go way down the beam line. And so you actually detect these in the far forward detector. And just to give you a sense of scale, like as Abe showed on Tuesday, this is something on order of like 40 meters long. So this is quite a impressive engineering part of the beam line. And so using this, you essentially are able to perform double spectator tagging to scatter off of the low momentum neutron. These are some projected results. So here, this paper here has some details about the study that was done, but the plots I'm showing here were actually updated relative to that publication for the HA detector proposal. And so on the left two are the A1N that you get at two different center of mass energies. So one 5 GeV electrons on 41 GeV helium. The bottom one is 18 GeV electrons on 166 GeV helium. And the point that what I want to draw your attention to is just look at how large the difference is between the uncertainty from the inclusive case with the uncertainty from the tagged case. They're very large improvements in what you're able to do. And then what you see on the right is just the full kinematic coverage. So on the right, on the horizontal axis is Q squared. On the vertical axis is the value of A1N with some X Bjork independent offset just to separate out the points. And so, as Abe mentioned on Tuesday, when it comes to the spin structure, like your sensitivity to the gluon contribution to the spin structure function comes from the Q squared dependence. So it's not just about pushing up down to the lowest X. You actually really want to map out the phase space so that you get sensitivity to the gluons as well. And so that's really shown here how well you can do that with this type of measurement.
So, sorry, can I ask you, so how is diffraction treated in here? Because if you're scattering two tagged protons, how do you know that one of them is not diffractively scattered? Like,
okay, I don't think that was considered in these projections.
There is a few percent diffraction,
Yeah.
so.
That was not, I'm fairly certain.
Well, sorry, what's the question?
Well, the question is, I mean, you're tagging
Mhm.
protons,
Mhm.
and the assumption is that these are spectator protons.
Mhm.
But one of them could, I mean, the particle could be
Yeah,
diffraction. So I guess some way of disentangling this.
I think that will be more on a physics background instead of experimental background, right? I mean, those you cannot remove. Those are physics process that.
Yeah, that you would have to simulate.
With the rapidity gap, so the X in this, would it fill the rapidity gap? If it wasn't a diffractive event?
But it could be a very large C, and then it's sort of
So-
diffraction or
Okay.
fracture functions or something.
So there are two possibilities, right? One is if you diffractive scatter off a proton and the proton stay intact and still go into far forward. And the other possibility is you have a DIS on the neutron breakup, but they could also target fragmentation and produce a proton, the final state. And then that final state proton will go into far forward. And then one of your real spectator was missing, and then you could also have background.
But if your electron is going into the central detector, where would that put, if you did have like your struck neutron like fragmented to a proton, would that end up in the far forward?
Yeah.
Okay.
It will. So basically we did this for the deuteron, but it should be the same for helium-3. It's just the same, because in principle, baryon number conservations, you could have some very forward baryon number, and that could be just a proton.
Okay. Yeah, so I think this was probably a fairly simple model where they were just considering, so that would have to be something that would be thought about incorrectly. So now going down the slope to the above the Fermi momentum, we'll now talk about 3 experiments that want to measure the structure of high momentum bound nucleons. And we'll start with the Deeps experiment. If I was giving this talk chronologically, this would actually be what I started with, because Deeps was like the pioneering tag DIS experiment. So I was going to give some motivation for why we want to study these, but I think Ellie did a good job of this yesterday. I mean, you have the high momentum tails populated by these short range correlated nucleons. There's a correlation between the SRC abundance and the magnitude of the EMC effect, which strongly suggests that there might be a connection here. I think Ellie showed all of this yesterday, so I'll just kind of quickly go through it. You can kind of describe the EMC effect by the universal modification of SRC nucleons, where you say, okay, if you're not an SRC, you just have the free structure functions. If you are an SRC, you have some modified structure function, and you're able to kind of consolidate all of the effects just into these SRC nucleons. So tag DIS is the first method that can actually definitively test this SRC EMC hypothesis. The EMC effect in deuterium is very small. Like here, you can see it's something like a 5% effect at largest. But SRC states are rare. And so as Ellie said yesterday, if you have a 5% effect that's essentially being caused by 4% of your nucleons, then you expect to see a very, very large effect, in those nucleons. And that's what these experiments are essentially trying to get at. So Deeps was the pioneering tag DIS experiment. It also ran in Jefferson Lab Hall B. Once again, it was the 6 GeV era, so they ran with 5.75 GeV electrons on a 5 centimeter liquid deuterium target. In this case, the scattered electron was detected in class, but also the spectator proton. So the spectator proton was also detected in class. And so this is the relevant part of the wave function that Deeps was trying to single out, looking at spectator momentum between 300 and about 500 MeV. One major issue with Deeps is that the kinematic coverage was very limited. So this is showing the W versus Q squared. And what you see is that the W almost entirely lies below 3. And most of the events have a Q squared less than 2, even by JLab standards. This is very, very low. And so you might even question whether or not this is true. You truly are in kinematics when you're sensitive to the quarks. But so this was kind of pretty problematic. But with a 6 GeV beam, they were very limited in what they could do. And so this is the result that they extracted. What their observable was this kind of double ratio of the bound neutron structure. So this would be the structure that they experimentally measured. And there's a ratio of the structure at x of 0.55 to the structure at x of 0.25. But then the double part of the ratio comes from the same ratio for the free neutron. So they took whatever the best calculation they had available for the free neutron structure, and then they formed this double ratio. And this is being plotted against alpha S, the spectator, the light cone momentum fraction of the spectator, and you see something that's mostly flat. I mean, you could argue that there's some kind of slope here, but they're really nothing really pops out as being kind of a smoking gun here. One thing that Deeps did look at though was that it seemed to validate what we discussed previously regarding FSI. So what's being shown here are kind of it's the same data, but shown in 2 different ways. On the left, for a low momentum bin and a high momentum bin, you are seeing the yield as a function of the cosine of theta PQ, which is the angle between the recoil spectator proton and the Q vector. And what you see is that when you compare the data, which are the points, to a PWIA calculation, which assumes no FSI in the solid line, you see that when you're at very backward angles, you get good agreement. And then once you get to kind of more perpendicular angles between P and Q, there's this large enhancement in the data that is not seen by the PWIA calculation. And then that's kind of shown, a complementary picture is shown here where it's shown versus the spectator momentum for two different bins in cosine theta PQ. And so you see that this one that's very, very far backward, you get really good agreement. But when you're at more perpendicular angles, you get this enhancement that's not seen in the PWIA. So this enhancement in data is, I think interpreted to be caused by final state interactions. And you see that you really avoid these if you're looking at very backward angles.
So this theory is aligned, right? The data has error bars, but the theory is
Right.
aligned.
Yeah.
And how do you really make the statement that there's any discrepancy?
That's a good point. yeah.
Obnoxious,
I mean,
but
right. I mean, my opinion, like for me, like theory curves, like it's either 0 or it's infinity. But I'm kind of joking.
I think,
but,
yeah, but, conservative assumption. is
Yeah,
if there's
yeah,
no
you're
error bar,
right.
then there isn't
And
anything.
the fact is that there's very limited data that can actually, that theorists are working with to actually try to make these statements. So I don't think that these constraints are that strong. Like, they're probably, if they did some sort of, estimate of uncertainties, you're right. It's quite possible that they would, overlap with the points.
So for electron scattering, the FSI can be quite substantial, and it depends strongly on.
Actually, let me backtrack. I was thinking the wrong way. This is so I think that actually predicting, like doing a calculation with FSI, that's very poorly constrained. And so people can, like theorists do their best and will say, okay, here's my calculation for the ratio of FSI to partial wave. But the FSI part is not really well constrained.
Yeah,
But
that
this
means
is the
error is large,
PWIA
right?
part, which I think is known, at least is known to a much better extent.
Oh, yeah, but your data has FSI, right? So you're comparing data that's measured, it has everything by definition.
Right.
And especially if you're saying that FSI is known to be not very constrained, that's sort of implying that the uncertainty of that line is probably large.
Or that you have a large effect from FSI at these.
Yeah, but
Examples,
I count PWIA say the error on that is small, but omitting FSI is part of the error. That's my point. And if
Well, right. Except I mean, I think that was the point I'm trying to make here is that if you say, okay, I'm omitting certain processes, the FSI processes, and you know that you're omitting that from your calculation. You're able to explain the data, at some angles, but not explain the data in other angles. And so, I mean, I think you're right
Yeah, I think you're
that,
making the
that some sort of band here would be like kind of saying how much freedom within PWIA do we have to wiggle this. But the point is, knowing that you're omitting FSI, how do you stack up against what you actually?
Yeah, so there's like, I don't know about these energies, but the energies that I've looked at, if you're sitting near the quasi-elastic, then the FSI is almost negligible.
Mhm.
But if you go away to the inelastic regime, the FSI can be totally overwhelming the PWA.
Yeah.
So it can be like 100% or more.
Mhm.
So, but this plot is showing this point. I mean, I guess the
Yeah, but that's sort of
PWIA
a-
is like almost very accurate. I mean, just from this, spectral functional, and it actually has a very small uncertainty. And then you compare it to data, which just has everything. So the big deviation shows you the hints of FSI.
Yeah, but I guess my point is then that this is well known from other measurements. This is not new, that FSI in electron scattering can be very.
But this is not quasi-elastic. This is deeply elastic.
Yeah.
Yeah, I mean,
For the quasi-elastic, that's usually where the FSI is known to be negligible, but
Right.
anything that's even not deep inelastic, but inelastic, as you go
So-
away.
but I think those plots the point of, sorry, I mean, actually let Tyler say it, but it's sort of like trying to map out where FSI in kinematic regions is larger or smaller. So we're trying to understand where this FSI dominates in what
Yeah.
kind of kinematic phase space. We know that it's overwhelming. I think the statement is we know it must be overwhelming at some point, but I think we don't know the quantitative where they are.
I can show you a point.
I mean, I don't, yeah, sure. But we also have, let's say, calculation of this, and this is not trivial. I don't think.
Yeah, I don't know about that. I mean, just what I'm talking about this because there's something that I was doing with a student when I was a postdoc. And we looked at this, and I guess a function of Q squared and omega, like where is the FSI large? What's the effect? And then this was like the point of the work was to see like about SRG of evolution, changing the potential. But part of that showed like where do you expect the FSI to be large?
Right, but then let's say if you have this Q square and omega, I guess the point here is we also need to consider the deuteron configurations, right? So the tag experiments basically have a control where your geometry really is, and that this geometry is largely affects your FSI.
Maybe I'm not making a very clear point. I think my point is don't look at PWIA unless you know that you are quasi-elastic. Otherwise, you need the FSI, and it's known that the plane wave approximation won't be described in the data. I think that's
But the whole point is not trying to describe the data, right? I guess the point is trying to see the difference to the data,
Right, I mean.
right? Is that
My understanding, even thinking about, future measurements, I'll mention a planned measurement for JLab that's supposed to run in a couple of years. We really do want to go to these perpendicular angles so that we can see if this is actually, if this pops out. Because I mean, we designed an entire experiment, being told, oh, if you go to backward angles, you'll minimize FSI. But it's actually nice to validate that assumption.
Okay.
And say if we look at the kind of transition from very backward spectators to kind of more perpendicular spectators, do we see the agreement with PWIA start to break down?
so okay. So you're looking for deviations beyond what's already known.
Right.
Okay.
Okay, so now I'll move on to the band experiment, and I'll spend a couple more slides on this because this is actually something that I spent a lot of time working on as a postdoc. So band stands for the backward angle neutron detector. It's a time-of-flight scintillator detector composed of over 100 scintillator bars that was then dropped upstream of the target in Jefferson Lab Hall B. So this is the class 12, the central detector, the forward detector, and this right here is band. The idea here is that so we have an electron beam coming in, scatters off of the liquid deuterium target. Our electron goes into the class 12 forward detector, and then we detect a recoiling spectator neutron in band. Band was a run group addition to run group B, so there was already a whole array of physics that was going to be done with this deuteron target. We just went in and put band in and collected data with them. And so this is just showing the kind of momentum range that we think that we're able to extract from this, from spectator momentum of about 0.15 up to about 0.4 GeV. Yeah. So before I go too far, I just want to give a kind of a shout out to the many students and postdocs that made very significant contributions to the results that I'm about to show. Here they are constructing the band detector. You can see right here, these are the scintillator bars, and there's a PMT on both sides here, because this right here is actually a hole in the detector for the incoming electron beam pipe. Because this had to be upstream of the target to detect backward going spectators, we had to make this gap in the detector to accommodate the incoming electrons. This is band positioned in Hall B. So here the beam would be coming from the lower right, pass through this hole, and interact with the target, which is somewhere like right here. And then this is the beginning of the class 12 detector, where we detect the scattered electron. So we, like the Deeps experiment, we're going to form some sort of double ratio where we compare to a theory calculation. And so we're actually using a non-asymptotic cross-section. When I say that, I mean that it just doesn't assume infinite Q squared by Mark and Christian. And just kind of very schematically, the cross-section depends on these parts. There's some kinematic factors. There's the deuterium spectral function, and then the free proton structure function is the input. So the critical thing here that I just want to make is that we're not assuming any modification of the bound proton. So when we take a ratio to this calculation, it's bound to free. So like our calculation assumes a free proton. And then what we did was we generated events with this model with QED radiation, and we did a full simulation in JON4. So these are just some pretty standard cuts on the electron in class 12. But most of this had already been established from previous run groups, and we just kind of made slight modifications for our running conditions. So these are all pretty standard. This is the results of our inclusive DIS analysis. So our first step before we started trying to complicate things with a spectator neutron was just look at the inclusive case. And so what you're seeing here is an area normalized comparison of simulation to data. We have some standard DIS cuts shown here. On the left is the X-Bjorken distribution with the simulation in red and the data and the points, and on the right is Q squared. And you see pretty good agreement there. And so this, for us kind of validates that we are doing a reasonable job simulating the electron part of class. So I wanted to just say a few words about the observable that we're looking at and why we're looking at this particular observable. So kind of standard method for extracting absolute cross sections is to use this yield ratio method, where you take the the ratio of your experimental yield to your simulated yield, and then you multiply it by whatever kind of theoretical Born cross section went into your simulation, and that gives you the experimental Born cross section. What we're doing is just kind of rearranging this and saying, okay, if we just look at the experimental to simulated yield, that's kind of like the ratio of our experimental cross section to our theory cross section. And so what we want to do is actually form a double ratio like Deeps did in bins of alpha S. So each one of these is kind of, we have a separate ratio for different bins in alpha S. This is pretty much identical to what Deeps did, where we're taking the experimental yield at 1 as a function of X prime, and then we're normalizing that to the yield at some fixed kinematic point. So the difference to what Deeps did is that we're actually looking at the X prime dependence in different bins of alpha, instead of just taking a ratio of high X to low X. We're actually going to look at the full X prime dependence. Now, one of the advantages to this double ratio is that you get a cancellation of systematics. So first of all, your luminosity for both data and simulation completely cancel. But then also, since we're doing this in bins of alpha S, what that means is that we're looking at neutrons that essentially have the same momentum. And so the neutron detection efficiency in our detector is a function of momentum. And so if we're taking this ratio for neutrons that within the width of the bin all have the same momentum, that means the detection efficiency also approximately cancels. We're choosing to normalize to X prime of 0.3. That's kind of arbitrary, but as we saw in the talk yesterday, most EMC measurements cross 1 at around X.3. So you can make the argument that this is kind of where the EMC effect is the smallest. And so this ratio is kind of equal to the double ratio of bound to free proton structure at 2 different kinematic points. So this is just kind of a picture. This is of the time of flight spectrum of our neutron. So this right here is our signal peak. This is where this carries all of the tagged information that we want to apply to our events. You see that it sits on top of this kind of almost constant off-time neutron background. I say almost constant because you can actually see that there's these little bunches here that are little peaks that are caused by the 4 nanosecond beam bunch structure of the JLab beam. So we actually were able to see that in our background, these little 4 nanosecond periods between the bunches. These are some comparisons of data to Monte Carlo for the tag DIS analysis. So the top, we applied this set of cuts here. The top 2 plots are kind of more geometric quantities. It's the angle, the polar angle and azimuthal angle of the recoiling neutron in the lab frame. And so this agreement here kind of shows us that we're doing a reasonable job of simulating the detector acceptance. So this is kind of a very geometric quantity. Then the bottom 2 is showing alpha S on the right, the light cone momentum fraction, and PT, the transverse momentum. And here transverse is relative to the Q vector. This is not in the lab frame. And so you see once again some pretty good agreement between our data and Monte Before I show the results, I want to make a comment about the relationship between X prime and X Bjorken. So this is for the events that go into the results I'll show on the next page. This is this is showing X Bjorken on the horizontal axis and X prime on the vertical axis. This diagonal line here is for alpha of 1, which would be a standing nucleon where X prime equals X Bjorken. And then these three red curves here show contours of higher alpha S, 1.3 to 1.5, and the corresponding neutron momentum for each of those contours. And so these are the two bins we're going to look at, alpha S of 1.3 to 1.4 and 1.4 to 1.5. The point here that I want to make is that there's kind of two ways that you can look at the X prime dependence. You could sit at a fixed X Bjorken and you could increase alpha S. And by increasing alpha S, you would be increasing X prime. And in that case, what you're doing is you're kind of looking at the same type of electron. The electron gives you the same X Bjorken, and you're actually looking at higher momentum neutrons. And that's how you're driving the X prime. But that's not what we're doing. What we're doing is we're actually fixing alpha S. We're looking at a bin of alpha S. And so the way we're driving X prime is by increasing X Bjorken. And so really all of the X prime dependence that we see here comes from you're looking at the same kind of population of neutrons, and you're just increasing the inclusive X Bjorken. And this is kind of a subtle point because for me personally, it's kind of comforting because I feel like we understand the scattered electron and detecting the scattered electron in the class 12 forward detector a little bit better than detecting neutrons, because neutrons are hard to detect. So this is the preliminary result for the tag double ratio. So the left plot is the lower alpha is alpha S between 1.3 and 1.4. The right is alpha S of 1.4 to 1.5. What you see is that the normalization of these points is like I said, kind of artificially fixed to be 1 at X of 0.3, because that's the kinematic point that we chose. And what you see though is that there's a large X prime dependent effect in these high alpha S protons. And so this is suggesting that there's some strong effect going on in these high momentum protons. One thing that's a little bit unfortunate is I talked about the reason why we chose to do this normalization in bins of alpha S because of the cancellation of systematics. You do kind of lose out on alpha S dependence. Like any absolute dependence of these points at alpha S is washed out because we're fixing this point at 1. But we think that we don't really have the ability to do anything more absolute. But so these are pretty promising results. They're currently under review. One thing by the class 12 collaboration. One thing that we would like to add to this is actually to go down to 1 bin lower in alpha S, so even lower momentum neutrons, and see if we kind of start to see this effect decrease. But that has not been approved to be shown as preliminary results. So the first question that we asked ourselves when we saw this large effect is, are these results consistent with existing inclusive measurement? Obviously this is not like a sufficient condition for saying, oh yes, our results are fine, because the whole problem here is that the inclusive measurements really don't do a good job of constraining these types of effects. But certainly, if our results didn't agree with inclusive measurements, that would be problematic. And so what we did was we took this, there was a grad student in our group at the time that had gotten quite talented at performing these kind of nuclear convolution fits to try to extract off-shell modification functions and extract neutron over proton, et cetera. What he did was he took the band result for one of the alpha bins, he added that into his fit that included other ratios of light nuclei. And what you see is that you're able to accommodate both the band result and all the inclusive results. And so this was a nice validation that even if this is a kind of a very impactful measurement, we're not violating any other data that currently exists. Another benefit to this is that it gives you a prediction for the bound neutron structure. If you have the deuteron and you have the bound proton, you really don't have that much wiggle room left with the bound neutron. And so that's what's being shown here is, this is the fit that was shown before for the proton. And this green curve shows a prediction for the neutron. So that's going to kind of be my segue into the last thing I'll mention, which is the LAD experiment. LAD is the large angle detector that will be installed at Hall C to perform the complementary measurement of proton tag DIS for neutrons. And so here we'll have a 1 microamp beam at almost 11 GeV scatter off of our deuterium target. We'll detect the scattered electron in either the high momentum spectrometer or the super high momentum spectrometer in Hall C. And then we'll have an array of scintillators at backward angles to detect the recoil proton and some gems for vertexing. So this is just a quick overview of the LAD hardware. One kind of cool thing about this experiment is that it's almost completely recycled. The proton detection is going to be performed with 5 panels of refurbished class TOF scintillators that will be used for proton ID and measuring the proton momentum. And then the proton vertexing will be done by 2 very large area gems that will be repurposed from the PRAD experiment. And so all of this equipment already exists, but it just needs to be kind of resurrected and installed. So LAD is a critical cross-check of these tag measurements in multiple ways. So the first one is, as I said before, inclusive measurements and band and LAD, you over-constrain the problem of bound nucleons in material. And so band and LAD together have to show consistent modification for the bound protons and neutrons. When I say that, I don't mean that they have the same modification, but that both of them have to be match what we see in inclusive. Another thing too is, as I mentioned before, we hope to achieve lower recoil momentum and lower recoil angle than band, which would let us, number one, try to see this effect go away as we go to smaller and smaller spectator momentum, but also kind of test our assumptions about FSI. If we start looking at this perpendicular region, do we see a huge enhancement relative to partial wave? We're expected to run in summer 2024. So in closing, tag DIS is just getting started. There's many more efforts for performing tag DIS both at JLab and at the EIC. There is the low energy recoil tracker alert with class 12 at Jefferson Lab, this is actually really cool. They want to look at DIS from helium-4 and actually tag on the A-1 system, so either helium or tritium. There's also going to be a what's called TDIS-N in JLab Hall C, which is going to perform a bonus style measurement of low momentum neutrons in deuterium. And then there's also multiple ways to perform tagging at the EIC to go beyond the neutron spin structure that I mentioned today. So in summary, tag DIS lets you kind of measure bound nucleon structure differential in kind of the nuclear wave function, which can be used to probe quasi-free neutrons and look at very highly virtual nucleons. Preliminary results from band and class 12 show a large modification of high momentum protons in deuterium, and there's a rich possibilities for a tag DIS program, both at JLab and at the EIC. So thank you.
More questions?
So can you go back to that ratio? For example, this one.
Yeah.
Can you explain it again what this ratio is? Because
Yeah.
either that a modification go down instead of go up.
Yeah, this is something that's been really puzzling to us, and we haven't, we've talked to many theorists about it, and I don't feel like we've gotten a good handle on the implications of what we're seeing. So what we're doing is we're taking what's being shown in that ratio is our experimental yield. So first of all, we're binning an alpha S.
Yeah.
And then, so for a given alpha S bin, we look at the yield as a function of X prime, normalized to the yield at X prime of 0.3. Okay. So that gives you one kind of basically the experimental X prime dependence relative to X prime of 0.3.
And that yield should decrease, right? As X goes up.
Not necessarily. No.
Why not? I mean, cross section drops from X 0.3
Okay,
to
yeah.
0.8.
Well, so see, it's going to be 1 at 0.3. I mean, but the problem here is that you're also conflating this with things like detector acceptance and stuff, and so that's
Modification.
yeah. So that's
Oh,
why.
so this is not correct?
Well, so that's what the Monte Carlo is for, And so, you divide by, so basically when you form this double ratio, this, where you take your the events generated with your theory calculation. And then you simulate them. This is what's accounting for things like detector acceptance and things like that. And so, I mean, like really, like you can kind of go through and use your Monte Carlo to explicitly extract individual corrections and then go back and apply those individual corrections to your measured yield. But at the end of the day, like.
Yeah, that I understand.
Yeah.
I actually just want a very general picture of what is actually plotting.
Yeah.
So I think it's the yield at a given x prime divided by the yield at x equals to 0.3.
Right, and then you do that separately for your
Measurement and the theory.
and the theory.
And theory has no EMC effect.
Right.
So, okay, this double ratio, a little bit different than like how we divided things, but it must be, so you think this going up, is that opposite of what you expect? No,
I
but
mean, I guess it might be opposite what we expect, but I don't really know how well we knew what to expect.
In the proposal,
Yeah,
when we proposed this experiment, we did calculation that Mark Schlickman did, and he assumed it's going down. But
right,
Another-
exactly.
that's about
yeah.
it.
Another thing too is that a lot of the proposal, I think the proposal actually showed things versus alpha S.
Yes.
And so what, if you look at things versus alpha S, I think what the proposal showed is that you had something that was kind of one at low X and then dropped below
Yeah, that's
Yes.
as a function of alpha S.
that's like
And-
what
and
we
so
do.
the
yeah.
issue though, is that we don't have, if we look at the ratio in this way, we don't have access to this alpha S dependence. So our measurement could actually be showing something that drops with alpha S, but because we're binning in alpha S and we're performing this double ratio, we're fixing the scale here. And so, and the problem is, I don't really think that we understand our systematics well enough to kind of try to do an absolute cross-section measurement that would be able to get the
So-
alpha S dependence.
Sorry, I'm too slow. Isn't that the EMC effect is showing up as a suppression of your cross section?
Mhm.
So when you take this ratio, and then your bound nucleon is on the numerator, so why is this going up? That is the only puzzle. It's not like how you bin it. I understand in alpha. So let's say in alpha S equals to 1.3, right? We expect that the nucleon has a high momentum, and we expect there will be EMC effect, very strong,
Right.
let's say. And then now you take the bound nucleon over the free nucleon, isn't that should be suppressed instead of going up?
That is what my naive expectation would be. I think what's happening here is that there are kind of very complicated multidimensional effects that are going on behind the scenes that just due to experimental constraints, we are not fully able to see this. So like I said, what would be great is to be able to map this out fully as a function of alpha S and X prime or something.
But let's clarify, it's not experimental effect. It's probably the kinematics mixed up that could drive this, right? It's not like that you didn't consider some detector effect, it was not corrected. Or because your double ratio basically cancel everything.
Right.
Okay.
That's one aspect. The other aspect is this is limited for photons. The EMC that you measure is combination of what happens to the photon and the photons. So it's not exactly the same.
But yeah, sure. But I think this is kind of mind blowing that the direction goes the opposite, right? I mean,
Yeah, that is.
Is that?
Can you go back one answer question? What is the Born? What does Born stand for here? Like the ratio.
Here?
This-
Yeah, just meaning like no, like this is the actual like vertex level cross section, not including radiative effects.
It's the simplest.
It's kind of like the one photon exchange.
Okay, so
really
sort
clean.
of, but then how the sigma Born experimental, how do you get to that? That's then my question. Because the diagram is a theory thing, but the experiment, the cross section is supposed to be see.
Well, right, so we apply all these higher order effects in our event generator. So we use like,
So the Monte Carlo is.
the Monte Carlo includes these QED radiative effects.
Okay, then I see. It might,
And so usually what's done, like, there's kind of two things that you can do here, and it's really a matter of taste. You can use these calculations of the higher order effects to correct your experimental yield, or you can just apply them to the calculation. And if you're taking the ratio, then both of those are equivalent.
yeah, right. I was just trying to understand what does it mean for an impact experiment. And the other question is, you mentioned there was a calculation of this, so is there like one interaction, or equivalently one momentum distribution for the neutron? Because at high momenta, as I've been tiring everyone making that point, you change the interaction, you change the momentum distribution, right? So if you're saying there was a theory calculation, a theory prediction for this, and then you're seeing something different, is there any theory that goes into your analysis where you would have to be careful to be consistent with what that prediction means?
So you're talking about.
Like your plot of the rho as a function of k. Like if you go to your summary, for example,
Oh, okay, yeah. So you mean,
Momentum
the
distribution.
momentum distribution, yeah, or this one, like any of
yeah,
these.
yeah, so,
Like
so.
if you take the absolute momentum distribution and those large momenta, you pick a different nuclear potential, you will get something different there. And
This
only thing you
this
have
should
to
be
be-
being taken into account when we
Okay.
actually sample from the spectral function. There's, the direction that the recoil is going depends on that. So
Yeah, more specifically, you mentioned there was like a prediction that would be going down, and you're doing the analysis, you see it go up, but that theory prediction and your analysis, wherever this went in, was it checked that this was actually the same?
oh, you mean like how sensitive are we to
Yeah,
the
to this.
yeah, we've used, so what actually goes into our analysis now is the wave function from AV18.
So it's, yeah.
We played around with the different ones and did not see, I mean, there's some small difference, but it's not like a large systematic.
Different ones,
They're different calculations.
yeah, different potential.
Yeah,
Yeah,
different
different potentials.
Like between,
And the low.
Yeah.
so including.
Yeah.
Okay.
So that is sort of like a theoretical uncertainties, right?
Yeah, so one advantage to kind of doing the neutron tag measurement is the proton structure function is really well known. So there's no kind of model uncertainty from F2P. For LAD, there's going to be some amount of uncertainty just from, like, if you compare to a calculation, what is the structure of the neutron? There's some model dependency.
So remind me, is that statistical driven that you can't plot it bin in as a function of alpha S?
I mean, it really has to do with that.
The kinematics?
Well, it has to do with detecting the neutron. That we maybe don't understand the efficiency of the detector as well as we would need to do like an absolute measurement. One thing that kind of complicated things is that this experiment was proposed and approved, this run group addition to put band upstream of the target, and then after that, class stuck a bunch of like electronics boxes upstream of the target. So like if you look at the right distributions, you can actually kind of see an imprint on our neutron detection, like where we lose events, based on this material that's upstream. So like we think we understand things well enough to kind of do this. We're essentially, we're not really relying that much on the actual. We're not really relying too much on the kinematics of the neutron itself, because we're binning an alpha S, and we're basically saying, do we have a neutron in this bin? And so that's kind of the extent that we're using it.
But how about PT? The neutron PT?
I think I
The
should.
tag PT? Yeah, maybe I use fast.
Yeah, here, right here. This is our PT distribution. Data on Monte Carlo.
So basically the PT going to higher PT is also limited.
Right, and that's limited by the acceptance, because this is a relatively small detector that's very upstream.
Yeah.
And so we really don't, and so that's one thing that we want to look at with LAD, is if we have the ability to go to larger PT, we want to see if we can spot FSI starting to take over.
Yeah, I've never worked on a fixed target experiment. So the whole thing
Yeah.
Like in
it's-
terms of acceptance is very different. For example, here that yeah, very cool, very cool. I still need to think about what's this racial being
Yeah.
opposite.
It,
Right, that was
that
the
is,
difference.
that is kind of, was a very puzzling.
Because
Feature.
yesterday, when Ali showed the plots, I thought it was just you guys take the ratio the other way around, right? The free versus the bound, and it's okay, that makes sense. Okay,
Thank you.
So, break. Back in 20 minutes, 10:40.
We still don't have the second speaker.